Hello everyone. You just saw a little bit of my new induction heater. This uses a full bridge inverter and it's not quite finished yet. I still want to run chilled water through these tubes, but you probably want to know how it's wired up. So today I'm going to show you a little bit about full bridge inverters. Alright, so in the past I've talked a lot about the IGBT chopper and I've talked some about the IGBT half bridge. And today, as I said, I'm going to talk a little bit more about a very important and very popular IGBT circuit. This is the IGBT full bridge or IGBT H bridge. Now this is for alternating current. This isn't to be confused with a reversible DC motor controller. This circuit is used in a very large amount of electronics, power electronics to be specific, whether it's a very high-end switch mode power supply, it could be an arc welder or a plasma cutter or an induction heater or even a solid state Tesla coil, a Tesla coil that uses electronic switches. So this is the most basic diagram. There are 4 switches and each of the 2 opposing switches will alternate. So when S1 negative will close, S2 positive will also close with it, and that will cause the current to flow one way through the load. And then the switches will turn off again, and then S2 negative would close, and then S1 positive would close, causing the current to flow the other way. This is what a diagram might look like of a full bridge inverter in a power supply, a DC to DC converter or an arc welder or a plasma cutter. Anything like that is what it would probably look like. This is what a resonant full bridge inverter would look like, and this would probably be used with an induction heater, or it may also be used with a Tesla coil, a solid state Tesla coil. Now you can make a full bridge inverter out of 2 dual IGBT modules. You can make a full bridge inverter out of 4 of the single IGBT modules, or you can buy an IGBT with 4 IGBTs in one package, configured as a full bridge inverter. This is the diagram that I use for my own full bridge inverter. You'll notice the 4 IGBTs and the 4 gate drivers. The gate drivers are HCPL 3120, and you'll notice that the LEDs are wired in anti-parallel, but there are 2 anti-parallel bridges connected together in parallel with each other. So if you apply an alternating current signal of low voltage to any one of these LEDs, the other corresponding LEDs of the other gate drivers will turn on at the appropriate times. So for example, the first bridge here has a positive and negative IGBT, and the second bridge also has a positive and negative IGBT. You'll notice because of the wiring that when the LED for the negative IGBT of the first bridge is activated, the positive IGBT of the second bridge will also be activated. When the alternating current reverses polarity from the input, these 2 would then turn off, and the positive from the first IGBT bridge will turn on, and the negative from the second IGBT bridge will turn on. During the first switching cycle, this would be the diagram. And notice I'm using electron flow, not current flow. The current flow would be the opposite, but it's still the same concept. So when the negative of the first bridge turns on, the positive of the second bridge also turns on, and the electron flow would move this way through the load and back around to the DC bus capacitor. Now the opposite happens when these 2 turn off, then the negative of the second bridge will turn on, the positive of the first bridge will turn on, creating an opposite flow through the load. So effectively, when we input a low voltage alternating current, the full bridge inverter will amplify the alternating current through our load. Now, take note, just as with any other gate driver, that you do need to have an isolated power supply for each one of them. If you don't have an isolated power supply for each one of them, then you will get a pretty nasty short circuit, and the DC bus capacitor will drain through the HCPL gate drivers, and it will make a pretty loud explosion. You should also put in some dead time, a time where none of the IGBTs are actually on. The reason why is these IGBTs, they usually turn on faster than they turn off. So if one turns on before the other one is finished turning off, it will lead to a short circuit and also an explosion. The dead time shouldn't be too long. If the dead time is too long and you have an inductive load hooked up, it may lose some of its charge, and that could lead to high currents and instability. Okay, so in the real world, a full bridge inverter would look something like this. You'll notice there are two IGBT modules and their snubber capacitors, the DC bus capacitor. C1 is positive, A2 negative, C2E1 would be the one output, and the other IGBT C2E1 is just the same. So they're both the same in terms of the bus connections. So let's see if it can focus. The G2 and E2 terminals are connected to this gate driver, the lower, that's the lower, and these control signals will be in parallel with this upper. So this lower IGBT on this bridge will turn on at the same time that the positive IGBT of this bridge will turn on. And you can see they all have their own individual gate drivers, and same with this one. When this upper IGBT of this bridge turns on, then the lower IGBT of this bridge will turn on. So the output will be alternating current. And the gate drivers HCPL 3120 have their standard wiring. These here, this is the power supply input, and these are the power supply input capacitors, and the gate resistor and the gate driver, and the output to the IGBT modules. And as I said, the inputs for the power supply, they all go to their own isolated power supply, and those are over here. So notice we've got two power supplies here and two power supplies here, and these are all isolated, so they can't have any connection with each other. They can't have anything in common. The grounds, the positive and negative on each one are all separated, and it has to be that way. And this is the LED inputs. This is where the alternating current will come in. So the lower stage of this bridge is going to have the same LED polarity as the upper stage for this bridge. And the same is true here. The upper bridge here will have the same polarity as the lower bridge here. So they need to be opposite of each other both ways. And remember, you don't want to have both of them on at the same time, because then you will get a short circuit, because then you will trigger both bridges at the same time and it will just short out. And the input cable right now is running audio. It uses a square wave signal from a personal computer output at 20 kilohertz, and it runs the induction heater that you saw running earlier. So that about does it for today. And one other thing, you can also use this for a single phase motor controller. Some motor controller manufacturers make a single phase motor controller, and sometimes it may use a full bridge instead of a three-phase bridge. But that's about it for today. If you have any questions, leave a comment, message me. Hope you learned something today, and thanks for watching.